July 1976, Wadi Besor, southern Israel. Among the dry rocks of the northern Negev, a microbiologist named Yoel Margalith and his colleague Leonard Goldberg are working their way along the edges of seasonal rain pools. Small bodies of standing water left behind by the winter floods, now slowly evaporating in the desert heat. Most pools are doing what desert pools always do at this time of year. They are crawling with mosquito larvae. Each pool is a nursery, dense with the wriggling forms of Anopheles, Culex, and Aedes species that have hatched in the warm, stagnant water. The two scientists are surveying for vector populations, counting, sampling, recording. Then, Margalith finds a pool that is silent. The water looks the same, the conditions look the same, but the surface is dotted with dead larvae. Every developmental stage, all of them lifeless. Something in this pool is killing every mosquito larva that hatches into it, and it is killing them quickly enough that the dead are accumulating faster than the live can replace them. Margalith collects soil from the pool bed and brings it back to Ben Gurion University. What he isolates from those samples and publishes the following year with Goldberg in Mosquito News is a previously unknown subspecies of a common soil bacterium. They name it Bacillus thuringiensis, subspecies israelensis. The world will come to know it as BTI. It is, by almost any objective metric, the most effective targeted insecticide ever discovered. It costs roughly $1.50 for 30 days of protection. The World Health Organization has approved it for use in finished, treated drinking water. After 36 years of large-scale field application across Germany, target mosquitoes have not developed resistance to it. Walk into any big box hardware store in your city. Count the shelves dedicated to mosquito sprays, electronic repellents, citronella candles, and DEET lotions. Now count the shelves featuring BTI. The shelf space tells a story. This video is about that story. One, a key cut by evolution. To understand why BTI matters, the first thing to understand is that BTI is not a poison. It is a biological mechanism that exploits a single specific feature of mosquito anatomy, and that specificity is the source of every advantage it has over chemical alternatives. When a BTI cell sporulates, it produces what biologists call a parasporal body, a small crystalline package containing 4 protein toxins identified in the literature as Cry4AA, Cry4BA, Cry11AA, and Site1AA. In their crystal form, these proteins are biologically inert. They cannot harm a fish, a bird, a bee, a dog, or a human being. Swallowed by any mammal, they pass through the digestive tract intact, dissolved by no enzyme, bound to no receptor. What they require to activate is an environment that almost nothing in nature produces. The midgut of a mosquito larva, where the digestive pH sits at approximately 11. This is extraordinarily alkaline. Human stomach acid runs around pH 2. A bee's gut sits near neutral. A fish's intestine ranges from slightly acidic to mildly alkaline. The mosquito larva's midgut is in a category of its own, a chemical environment evolved for one purpose: to break down the tough plant detritus that suspended feeding larvae filter from stagnant water. When a larva ingests the BTI crystal, the alkaline environment dissolves it. Gut proteases then cleave the released protoxins into their active forms. 3 of the 4 toxins, the Cry proteins, bind to specific receptor sites on the cells of the gut wall. They form pores. The cells swell, rupture, and die. The 4th toxin, Site1AA, does not need a protein receptor at all. It inserts directly into the lipid membrane of gut cells and, in a feature researchers have only recently fully mapped, it serves as a substitute receptor for the cry toxins when the larva tries to evade them. This is the structural reason resistance has not emerged in the field. Even if a larva mutates to lose one cry receptor, site 1A, hands the toxin a key to the door anyway. The mosquito would have to mutate 4 independent defense mechanisms simultaneously to survive a BTI exposure. Across 49 years of use across multiple continents, no wild population has done so. Within 24 hours of ingestion, the gut is destroyed. The larva stops feeding. Death follows from starvation and septicemia. Field studies in Burkina Faso, published in the open-access journal Malaria Journal, recorded 100% mortality of Anopheles larvae within 24 hours across all tested concentrations. Studies in northeastern Tanzania reported 91 to 100% mortality in the same window. Lethal concentration values for Aedes aegypti, the vector for dengue, Zika, chikungunya, and yellow fever, measured as low as 0.052 milligrams per liter. This is not a pesticide in the conventional sense. This is a key cut by evolution to fit one lock, the lock that happens to belong to the deadliest animal in the world. The World Health Organization estimates mosquitoes kill more than 700,000 people every year. Malaria alone, transmitted by Anopheles species, accounts for roughly 600,000 of those deaths. The bacterium isolated from a desert pool in 1976 destroys the larva that grows into the mosquito that delivers the parasite that causes the disease. It does so without harming the mammal, bird, fish, amphibian, or beneficial insect that happens to share the water. 2. The 36-year experiment. The largest field test of BTI in history was not a single study. It was an entire river valley. In 1980, the German Mosquito Control Association, known by its German abbreviation KABS, began routine treatment of mosquito breeding habitats along the Upper Rhine Valley. The target was Aedes vexans, a floodwater species that had plagued the riverbanks for centuries. The treatment area expanded year after year. By the time researchers published a peer-reviewed assessment in 2019 in the Journal of the American Mosquito Control Association, KABS had applied roughly 5,000 metric tons of BTI formulations across approximately 400,000 hectares. 36 years of continuous, large-scale, single-tool pressure on a wild mosquito population. Under comparable pressure, conventional chemical insecticides have failed within years. Pyrethroid-resistant Anopheles populations now span entire continents. DDT resistance was documented within a decade of widespread use. Carbamate and organophosphate resistance followed similar timelines. Every chemical class introduced for mosquito control in the 20th century has been outpaced by mosquito evolution. The KABS researchers tested Aedes vexans larvae from 6 treated zones along the Rhine and 3 untreated control zones around Lake Constance. They ran the susceptibility bioassays following World Health Organization guidelines. The result was unambiguous. Resistance ratios across all populations ranged from 0.80 to 1.12, statistically indistinguishable from baseline. After 36 years of use, the larvae in the treated zones were no less susceptible to BTI than the larvae that had never encountered it. In 2 of the populations, the treated zones were actually slightly more susceptible than the untreated controls. The yearly mosquito reduction across the treated area exceeded 90%. No documented harm to honeybees, fish, amphibians, or aerial insectivore birds attributable to BTI itself. The Upper Rhine Valley today is the closest thing humanity has to a multi-decade controlled experiment in biological mosquito control. The result is a tool that works, has always worked, and shows no signs of stopping. So here is the question this video exists to answer. Why has a 49-year-old discovery, endorsed by the World Health Organization for use in drinking water, proven across 36 years of continuous, large-scale field application, costing roughly $1.50 per month of protection? Why has this discovery never reached the awareness of the average consumer? The honest answer requires looking not at BTI itself, but at the structure of the market that decides what reaches a consumer shelf. 3. The economics of absence. The global pesticide industry generated approximately $45.7 billion in revenue in 2022, according to Allied Market Research, with projections exceeding $90 billion within the next decade. Specialty pesticides alone, the category that includes consumer mosquito sprays, accounted for over $26 billion in 2024. These are the numbers that determine which products receive marketing budgets, which products receive shelf placement, which products the average homeowner has heard of at all. BD competes in none of those numbers, and the reasons are structural. First, BD cannot be patented. It is a naturally occurring soil bacterium, public domain since the original Goldberg and Margalith papers were published in 1977. Any manufacturer can produce it. Any retailer can stock it. There is no exclusive license to defend, no research recouping period to protect, no premium price floor to maintain. The price tracks manufacturing cost, which is why a 30-day mosquito dunk retails for under $2. Second, a single application protects standing water for 30 days. There is no subscription model. There is no weekly aerosol bottle replaced at $15 apiece across a summer. A homeowner using BTI correctly might spend $12 across an entire mosquito season. That is not a revenue stream. That is a single transaction. Third, BTI requires consumer education before it can be sold. A pyrethroid spray sells itself. Point, spray, watch the mosquito drop. BTI demands that the consumer understand mosquito biology. Where do mosquitoes lay eggs? Why does targeting larvae matter more than targeting adults? Why is a bucket of leaf-filled water in the corner of the yard suddenly an asset rather than a liability? Each of these is a small act of teaching. Teaching costs money. No company has any reason to spend money teaching consumers about a product the company cannot charge a premium for. Fourth, BTI does not fit the economics of retail shelf placement. Big box retailers prioritize products with high margins, frequent reorder cycles, and recognizable brand marketing. BTI offers low margins, monthly reorder at best, and almost no consumer brand awareness. The shelf math does not work. So BTI ends up classified as professional or agricultural product, sold to municipal mosquito control districts, distributed through specialty catalogs, available online to anyone who already knows to search for it. The classification is not a conspiracy. It is what happens when a product's profit margin doesn't justify the marketing spend required to educate retail consumers about an unfamiliar mechanism. But the result for the homeowner is identical to suppression. They cannot buy what they have never been told exists. They cannot use what they have never been taught to apply. And they will continue spending $200 per summer on aerosols that evaporate by morning, because those aerosols are what the system is designed to put in front of them. This is not suppression. This is something colder. This is indifference. The most effective mosquito control agent ever discovered sits at the bottom of a market hierarchy that has no incentive to elevate it. Every August, when the dengue maps light up red across Southeast Asia and Latin America, when the malaria case counts climb in sub-Saharan Africa, BTI is doing exactly what it has always done, quietly, in the catalogs of municipal vector control districts, in the spore tanks of public health departments, far from the consumer aisle. It is fully capable of doing more. It will not be allowed to do more by the consumer market because no commercial actor stands to profit from teaching it. Who benefits from this arrangement? Not the homeowner paying $15 a bottle for an aerosol that lasts a weekend. Not the family in the dengue zone. Certainly not the bacterium itself, which is indifferent to whether anyone uses it. The arrangement benefits the structure that produced it, and structures, unlike conspirators, cannot be brought to account. 4. The Ovitrap as engineering principle. The technique most often paired with BTI in modern vector control is the oviposition trap, or Ovitrap. It is a deceptively simple structure. Standing water, organic matter, typically dead leaves or grass clippings, and a measured dose of BTI. Public health researchers have studied the configuration extensively because of how cleanly it inverts mosquito reproductive behavior against itself. A gravid female mosquito does not lay eggs randomly. She selects breeding sites based on chemical cues, dissolved organic matter, larval pheromones, certain microbial signatures. Stagnant water rich in decomposing leaves is, to her sensory system, a beacon. The Ovitrap is engineered to be a more attractive beacon than anything else within her flight range. She will fly past clean bird baths, swimming pools, and rain barrels to deposit her eggs in the Ovitrap. The eggs hatch, the larvae feed. The BTI crystals dissolve in their alkaline guts. They die. The structural elegance is this. A traditional adulticide spray reduces the visible mosquito population for a few days, then evaporates. The mosquitoes that were elsewhere when the spray was applied, the vast majority, are unaffected. The Ovitrap, by contrast, does not reduce the adult population directly. It reduces the next generation. Each female that selects the Ovitrap as her breeding site produces 0 offspring. Repeated across a yard, a block, or a city, the breeding population collapses without a single adult mosquito being sprayed. This is why municipal vector control districts in Florida, in Singapore, and in parts of Brazil have built dengue suppression programs around BTI ovitraps rather than adult fogging. The economics scale, the biology scales, the public health outcomes scale. The Cambodian National Malaria Center, working with Vectobac WG, a BTI formulation reviewed by the WHO Pesticide Evaluation Scheme, measured significant reductions in Aedes aegypti density and dengue transmission rates in field trials. What does not scale is the consumer marketing, which is why almost no homeowner watching this video has ever heard the term Ovitrap before today. 5. Honest limitations. A documentary that presents any tool as flawless is a documentary that should not be trusted. BTI has real limitations. They do not erase its value, but they define the boundaries of its usefulness. BTI kills only feeding larvae. It does not affect mosquito eggs, pupa, or adult mosquitoes. A homeowner whose yard is already swarming with adult mosquitoes will see no immediate relief from a BTI application. The effect is generational, measured across weeks, not hours. BTI biodegrades quickly. Sunlight, organic matter, and water chemistry break it down within 30 days under typical conditions. It must be reapplied. A single dunk dropped in a rain barrel at the start of summer will not last until autumn. The efficiency of the product is also its limitation. A tool that fades cleanly from the environment also fades from the rain barrel that needed protecting. BTI is ineffective in flowing water. Streams, ditches with active drainage, and well-circulated ponds dilute the bacterium too quickly for larvae to ingest a lethal dose. It works in stagnant water, buckets, bird baths, blocked gutters, tire piles, the puddles that collect in tarps and unclean saucers under flower pots. BTI is not a perfect ecological null. While it is harmless to mammals, birds, fish, amphibians, bees, and the vast majority of beneficial insects, peer-reviewed studies in the Upper Rhine Valley have documented reduced abundance of non-biting midges, Chironomidae, a closely related family of Diptera with similar gut chemistry in heavily treated wetlands. The effect is modest compared to the impact of synthetic insecticides on entire food webs, but it is real and worth acknowledging. BTI requires the user to find every breeding site. A single missed bucket, a single forgotten saucer under a flower pot can produce enough mosquitoes to undermine the effort. It rewards thoroughness. It punishes carelessness. The tool works only as well as the survey of breeding sites that precedes it. These limitations are real. They are also why BTI is a tool, not a miracle. 6. What BT does not replace. This video has been critical of the consumer pesticide market. It has not been critical of every alternative to BTI, and the distinction matters. DEET, the active ingredient in most personal mosquito repellents, has been studied for over 60 years. It does not kill mosquitoes. It disrupts their olfactory ability to find a host. The Environmental Protection Agency has re-registered it as safe under labeled conditions. For a hiker in a malaria-endemic region, for a soldier deployed to a tropical zone, for a child playing in a backyard during peak mosquito hour, DEET on exposed skin is a legitimate, evidence-backed defense. It is not a substitute for BTI. It is a complement. They protect at different stages. Pyrethroid-treated bed nets distributed at scale across sub-Saharan Africa are credited by the World Health Organization with preventing more than 2 billion malaria cases between 2000 and 2023. They work. They are cheap. They have flaws. Pyrethroid resistance is now widespread. But the public health record of insecticide-treated bed nets is among the most consequential in modern medicine. Window screens, mosquito-proof clothing, environmental sanitation, larval source reduction by physical drainage. All of these are tools that have collapsed mosquito-borne disease across the developed world over the past century. Malaria was eliminated from the United States in 1951, not by a single magic bullet, but by a combination of drainage, screening, treatment, and surveillance. BTI does not replace any of them. It targets a different stage of the mosquito life cycle. It works at the breeding site, not at the moment of biting. A complete defense against mosquito-borne disease uses multiple tools at multiple stages. The argument is not that BTI is the only answer. The argument is that BTI is the answer that has been quietly missing from the consumer toolkit, while the others have been heavily marketed. Closing. The private experiment. In 2003, the Tyler Prize for Environmental Achievement, sometimes called the Environmental Nobel, was awarded to Yoel Margalith. The Tyler Executive Committee credited his discovery with having saved millions of lives with minimal environmental impact across the decades since the desert pond. Millions of lives. From a soil sample taken at the edge of a silent pool in Wadi Basor 27 years earlier. The structure of the market that decides what reaches a consumer shelf is unlikely to change. No corporation will suddenly decide to spend $50 million teaching homeowners about a bacterium it cannot patent. The economics will not shift. The classification will not be reversed. The shelf space at the big box garden center will continue to be dominated by aerosols and electronic devices that solve the symptom for an evening. But the structure of the market does not require permission to be bypassed. A bucket, some leaves, a $2 dunk. An Ovitrap is, in essence, a private experiment that no commercial actor was ever going to run on behalf of the consumer, because there is no money in running it. The invitation at the end of this video is straightforward. Set up a single Ovitrap in a shaded corner of a yard, balcony, or rooftop. A 5-gallon bucket, a handful of dead leaves, a quarter of a BTI dunk dropped in. Document its condition over the next 30 days. Return to the comment section below this video and report what was observed. Number of dead larvae, change in adult mosquito presence, local weather conditions, general location. Comment by comment, the section beneath this video can become something the consumer pesticide industry has never had any incentive to produce. A public, distributed, real-world dataset on the effectiveness of the cheapest mosquito control tool ever discovered. Margalith found his answer in a desert pool that no one else had thought to examine. The next dataset on BTI's real-world performance will not come from a corporate laboratory. It will come from whoever is willing to pay attention to a bucket of water in a backyard. The shelf space tells a story. The comment section can tell a different one.